You know those big, beefy exam questions? The ones worth a ton of marks that can make or break your grade? Well, they might look a little scary, but they're actually a massive opportunity to rack up points. Today, we're going to take one of those, a 14-mark GCSE Physics question, and pull it apart piece by piece so you know exactly how to ace it. Okay, let's get right into it. This single question is like a mini test all on its own, covering optics, electromagnetism, and mechanics. We're not just going to find the answers, we're going to really understand the physics behind them. And more importantly, we'll see exactly how to lay out our answers to make sure we get every single mark. So, first up, we're dealing with a security lens. The question tells us it's a concave lens, and that's our cue for a classic ray diagram. This first part is worth 3 marks, so let's build this thing step by step. Right, first things first. To grab that first mark, we draw our first ray of light. You start at the very top of the object, our visitor, and draw a straight line parallel to that central axis until it smacks into the lens. Now, because this is a concave lens, the ray bends outwards, or refracts, so it looks like it's coming from the principal focus, that point F, on the same side as the visitor. For our second ray, and our second mark, the rule is super simple, probably the easiest one to remember. You draw another straight line from the top of the object, but this time, you aim it right through the dead center of the lens. This ray is special. It just goes straight through. No bending, no nothing. Okay, time for the final mark on this diagram. We need to find where the image forms. If you look to the right of the lens, our 2 rays are moving apart, so they're never going to cross paths over there. So what do? We trace that first bent ray backwards with a nice dashed line. The spot where that imaginary line crosses our second ray, that's the top of our image. Just draw a little arrow down to the axis and boom, diagram complete. So, what was the point of all that drawing? To figure out the properties of the image. And as you can clearly see, it's a virtual image because we had to trace rays backward to find it. It's upright, meaning it's the right way up, just like the visitor, and it's diminished, which is just a fancy way of saying it's smaller than the actual object. Okay, on to the next part. This is a quick 1-mark question. It's asking what happens to the size of that image we just drew if the visitor, our object, moves farther away from the lens. And the answer is pretty straightforward. The image gets smaller. It decreases in size. Think about it. As the person moves further away from a concave lens, that virtual image we drew actually gets closer and closer to the focal point, making it look even tinier. Ticking that box gets you the mark. Simple as that. All right, let's switch gears. We're moving on from the world of light rays into electricity and magnetism. Now we're going to look at how the electronic door lock actually works. So let's break down this contraption. What we've got is a pretty simple circuit, right? A switch and a battery are powering a solenoid. That solenoid is wrapped around an iron bolt, and there's a spring holding the bolts in place. The whole secret to the next few marks is understanding how all these parts work together. Question 4.3 asks what the bolt should be made of. The choices are aluminum, brass, copper, and iron. The key here is we need something that's going to be strongly attracted to a magnet. And the answer has to be iron. Why? Because iron is a magnetic material. That means the solenoid can easily turn it into a magnet when the power's on. But, and this is super important, it doesn't stay a magnet forever. You need a lock that can actually, lock and unlock. Now, before we get into the nitty-gritty of how the lock works, let's just make sure we're all on the same page about what a solenoid is. It's really just a coil of wire. That's it. When you run an electric current through that coil, it creates a magnetic field, basically turning it into an electromagnet. This little trick is the heart and soul of this door lock. Now, for the big 3-mark explanation in question 4.4. To get all the points, you've got to tell the story in the right order. First, you close the switch, which completes the circuit and lets the current flow. Second, that current zipping through the coil creates a magnetic field, turning the solenoid into an active electromagnet. And finally, that magnetic field yanks on the iron bolt, attracting it and pulling it out of the doorframe. And just like that, the door's unlocked. Next up, the exam asks for 2 ways you could make the pull on the bolt even stronger. To get these marks, you just need to list any 2 of these options. You could pump more current through the wire, you could wrap more turns of wire around the coil, or you could stick an iron core inside the solenoid. Any of those will create a stronger magnetic field and a stronger pull. And here we are, the final part of the question. It's calculation time. This is a 4-marker, and it's all about that spring that pulls the bolt back into place. Our mission? To to calculate its spring constant. The bit of physics we need to pull out of our toolbox here is Hooke's law. Your formula sheet will tell you that the force on a spring equals the spring constant, which we call K, times its extension. But we're not looking for the force, we need to find K. So your very first move is to rearrange that formula to get K all by itself. All you have to do is divide both sides of the equation by the extension, E. This gives us our new formula. K equals F divided by E. And hey, just showing you can do this simple bit of algebra often bags you a mark all on its own. Now listen up, because this is so important. This is the classic trap where people lose easy marks, the units. The force is given in newtons, which is great. That's the standard unit. But the extension is in centimeters. For our formula to work properly, it has to be in meters. So we've got to divide 1.50 by 100 to get 0.0150 meters. Don't forget this step. All right, now it's just a matter of plugging the numbers into our rearranged formula. We slot in 2.88 newtons for the force, and our freshly converted extension, 0.0150 meters, for E. You can see exactly how it looks on screen. And when you punch that into a calculator, it gives us our final answer, 192. And don't forget the units, newtons per meter. So by showing your formula, the unit conversion, your substitution, and the final answer, you've just locked down all 4 marks. Beautiful. And we're done. That's it. 14 marks safely in the bag. We've worked through lenses, we've tackled electromagnets, and we've done some calculations with springs. Let's do a super quick recap of the key physics ideas we used to solve this whole thing. Wow, this one question was a real workout, wasn't it? We jumped from optics for the ray diagram to electromagneticism to figure out the lock, and then into mechanics for the spring calculation. It's the perfect example of how all these different topics in physics are actually connected in real-world gadgets. And I'm going to say it one more time, always watch those units. I think the biggest lesson here is that even a monster of a question can be conquered if you just break it down into smaller, bite-sized pieces. And the physics we used for this door lock, it's not just stuck in an exam hall. It's in electric motors, it's inside your speakers, it's even in those giant electromagnets you see in scrapyards. So my question to you is, where else do you see these ideas in action around you?